How are you everybody? How are you today? This is lecture number 11 in advanced mathematics for 4th year statistic English section, Benha University 2020. This lecture related to some basic in mathematics. This lecture is very important to understand some basics related to mathematics, and I want from every student to study this lecture very closely to understand what I want to say. Some basics in mathematics. This lecture is related to some basic in mathematics, in pure mathematics, and this lecture is very important to know what is the meaning of binary code and the hexadecimal code and index 10 and x index 2, and how can we convert between index 10 and index 2 and vice versa. We will see this in our lecture. Now, what about review of algebraic techniques? Laws of indices. Consider the product 6 by 6 by 6 by 6 by 6. This may be written more compactly as 6 to the power 5. We call the 5 the index or power. The base is 6. Similarly, y multiplied by y multiplied by y multiplied by y may be written as y to the power 4. Here, the base is y and the index is 4, or the power is 4. Example, write the following using index notation. Minus 2 multiplied by minus 2 multiplied by minus 2 may be written as a minus 2 to the power 3. 4 multiplied by 4 multiplied by 4 multiplied by 5 multiplied by 5 may be written as 4 to the power 3 multiplied by 4 by 5 to the power 2. Triple y and 4 divided by 4x may be written as y to the power 3 over x to the power 4. Note that minus a multiplied minus a equal a multiplied by, since the product of two negative quantities is positive, so a multiplied by a equal minus a multiplied by minus a equal a to the power 4. Also, b minus b multiplied by minus b equal minus b multiplied by equal minus b to the power 3, hence, and so on. This is what about index or power. Dividing expressions involving indexes. Consider the expression 4 to the power 5 over 4 to the power 3. 4 to the power 5 over 4 to the power 3 must be written as 4 to the power 2, because we cancel 3 4 in the numerator and 2 4 in the denominator. This serves to illustrate the second law of index, which is a to the power m over a to the power n equal a to the power m minus n. When expressions with the same base are divided, the indexes are subtracted. Simplify. 5 to the power 9 over 5 to the power 7 must be 5 to the power 2. And so on. Y to the power 6 over y equal y to the power 5. X to the power 5. X to the power 9 over x to the power minus 5 equal x to the power 9 multiplied by x to the power 5. It's obviously. Consider the expression 2 to the power 5 over 2 to the power 3. 2 to the power 3 over 2 to the power 3 must be equal to the power 0 equal 1, and so on. A to the power 0 equal 1. Any expression raised to the power to the index 0 must be equal. Negative instances. Consider the expression 4 to the power 3 over 4 to the power 5 must be equal 4 to the power 3 multiplied by 4 to the power minus 5 equal 4 to the power minus 2 equal 1 over 4 to the power 2. Alternatively, using the second law of instances, we have 4 to the power minus 2, and so on. Thus, we are able to intercept the negative index. The sign of an index changes when the expression is inverted. In general, we can state a to the power minus m equal a to the power m minus 1, m to the power m, a to the power m equal 1 over a to the power minus m. This what we stated about negative ends. How are you everybody? How are you today? This is lecture number 11 in advanced mathematics for 4th year statistic English section, Benha University 2020. This lecture related to some basic in mathematics. This lecture is very important to understand some basics related to mathematics, and I want from every student to study this lecture very closely to understand what I want to say. Multiple answers. Consider the expression 4 to the power 3 to the power 2. This may be written as 4 multiplied by 3 multiplied by 4 multiplied by 3 equal 4 to the power 3 plus 3 equal 4 to the power 6. So that this illustrates the third law of ends, which is a to the power m all to the power n equal a to the power m multiplied by n. Note that the answers m and n have been multiplied. Write the following expression using a single ends. 3 to the power 2 to the power 4 equal 3 multiplied by 2 power 4 equal 3 to the power 8. 7 to the power minus 2 to the power 3 equal 7 to the power minus 6. X to the power 3 to the power minus 3 equal x to the power minus 6. X to the power minus 2 to the power minus 3 equal x to the power 6. Consider this expression 2 to the power 4, 5 to the power 2, all over the power 3. We see that 2 multiplied to the power 4, 2 to the power 4, 2 to the power 4, 5 to the power 2, 5 to the power 2, 5 to the power 2 equal 2 to the power 12, 5 to the power 6. This illustrates a generalization of a third law of ends, which is a to the power m to the power n to the power k equal a to the power mk b to the power nk. Now remove the brackets. 2x to the power 2 to the power 3 equal 8x to the power 6 minus 3y to the power 4 to the power 2 equal 9y to the power 8. X to the power minus 2 multiplied by y to the power 3 x to the power minus 6 y to the power 3. It is very easy to calculate. Number bases. The decimal system of numbers is in common use is based on the 10 digits 0, 1, 2, 3, 4, 5, 6, 7, 8 and 9. However, other number systems have important applications in computer science and electronic engineering. In this section, we remind the reader of what is meant by a number in the decimal system and show how we can use powers or answers with base of 2 and 16 to represent numbers in the binary and hexadecimal system respectively. We follow this by an explanation of an alternatively binary representation of a number known as binary coded decimal. What is the meaning of binary coded decimal? The decimal system, the numbers that we commonly use in everyday life are based on 10. For example, 253 can be written as 200 plus 50 plus 3, 2 multiplied 100 plus 5 multiplied 10 plus 3 to the power 1, 3 multiplied by 1, 2 to the power 10 to the power 2, 5 to the power 10 to the power 2, 3 to the power 10 to the power 0, 3 multiplied by 10 to the power 0. So that the base is 10. In this form, it's clear why we refer to this as a base 10 number. When we use 10 as a base, we say we are writing in the decimal systems. Note that in the decimal system, 3 are 10 digits from 0 up to 9. You may recall the phrase hundreds, tens, and units, and as we have seen, these are simply powers of 10. To avoid possible confusion with number using other bases, we denote numbers in the base 10 with a small subscript. For example, 5192 10. 5,000 plus 100 plus 90 plus 2. 5 multiplied by 1,000, 1 multiplied by 100, 9 multiplied by 10, 2 multiplied by 1. 5 multiplied by 3 to the power, by 10 to the power 3, 1 multiplied by 10 to the power 2, 9 multiplied by 10 to the power 1, 2 multiplied by 10 to the power 0. Note that in the previous line, as we move from right to left, the powers of 10 increases. This is what we mean a base 10, decimal system. The binary system uses the number 2 for its base. A binary system has only 2 digits, 0 and 1, and these are called binary digits or simply bytes. Binary numbers are based on powers of 2. In a computer, binary numbers are usually stored in groups of 8 bytes, which we call a byte. Converting from binary to decimal, consider the binary number 11010112 binary. As the base 2, this means that as we move from right to left, the position of each digit represents an increasing power of 2 as follows. 110101 to the index 2, this mean binary code. So that hence 110101 to the binary 2 and 53 to the power 10 are equivalent. Convert the following decimal 111 binary 2 101010 binary 2 to the decimal 10 to the base 10. So that 111 binary 2 equal 15 binary equal 15 base 10. 101010 binary 2 equal 42 to the base 10. This is what I will state it in this lecture, and see in the last lecture in online courses number 12. Thank you for everybody. See you in the next lecture in the faculty and on the faculty website. Thank you for everybody.